So chapter 11, working with refrigerants. Okay. So we're going to check refrigerant charge by determining a system's superheat or subcooling, implement both passive and active refrigerant recovery procedures, charge a system with an inert gas to pressure test for leaks, carry out refrigeration system leaks repairs using either epoxy resin or brazing. I know we talked about a little bit of this stuff last week, and I'm definitely going to keep informing you guys of different techniques, different things that I've run across in the field. Like this last thing, the epoxy resin. Not a big fan of the epoxy resin. If you're going to do any type of repair, I prefer brazing. The resin may or may not hold, and so I don't want to take that chance, especially when I'm working on pretty big systems or high pressure applications. So evacuate a refrigeration system using both deep vacuum and a triple evacuation method. Charge specific amount of refrigerant into a system as either a liquid or a vapor, and follow approved safety procedures when recovering and charging refrigerant. So refrigerant charge. A proper charge is necessary for proper operation. The reason we properly charge a system is so that the system operates like it's supposed to. If we were to undercharge a system, we're not going to have enough refrigerant in that system for it to remove the heat that it's supposed to. So the system's going to work that much harder trying to maintain a set temperature. If we have too much refrigerant, well, then the system's not going to be able to remove any heat as well, because it's just going to be so bogged down with refrigerant, and so it's not going to work properly. So we want to have a properly charged system. The same thing applies when we're sizing equipment. We want to make sure that our equipment is sized to the specification or to the place that it's going in. Just because we have a 2-ton system in a home doesn't mean that a 2-ton system is what is required. Sometimes we may need a 2.5-ton system. We need to upsize. We may have to go lower. So we do the thing called a manual J. Basically, what it is, it's a type of sheet that you end up doing. You measure out the home, you put in all these different values that you've measured, and so you're talking about window size, ceiling height, walls, wall insulation, what are the floors made of, how tall is the building, all this stuff. You put it into a program, and it spits out a number and says, hey, you know what, this is exactly what the specifications are for that home. So it's a little bit more off topic, but I'm just going to show you the right way of actually doing this. I'm just going to open up a project that I've done for some people, and so here's a good one. So the thing that comes about with doing a manual J is it's going to tell you what your heat load is of the building. That's going to be our primary concern, and we want to be able to remove that heat load. You may have two identical buildings that are sitting right next to each other. One may have a big tree covering the top of it, and it has tons more insulation, new windows, and the other building may be sort of decrepit, falling apart, and you're going to have two different size loads. Even though they're the same building, you're going to have two different types of systems. So the only way of really doing it correctly is to do a manual J. Depending on who you work for, they may want to do this, they may not. The governing bodies, they want you to do it every single time you do an equipment replacement, because we're going to put in the right size. Why is that important? All right. Why is putting in the right size equipment crucial? Well, first off, we're going to save energy. All right. If we put in too large of a system, it's going to operate way too hard, just drawing too much electricity because it's such an oversized piece of equipment, and then it's going to shut off very quickly. And then it's going to turn back on, and it's going to shut off. So the problems are twofold. If we size our equipment incorrectly on the AC side, we're going to have a thing where we're going to blow way too much cold air into a space, and we'll never properly remove the moisture, all right, the humidity. So we're going to have a really cold environment that is muggy. and that's just miserable. So when we dial in our systems, we dial them in so that they're both removing latent heat and sensible heat. All right, we're going to remove the moisture, and we're going to we're going to make the space cool. If we had too big of a system, it's just not going to work. So, us Americans, we always think that bigger is better. Not in the HVAC world. I would almost undersize a system, have it run just a little bit harder to, cool off that space or dehumidify rather than to oversize. The same applies to furnaces, all right? If I have too large of a furnace, it's going to shoot a ton of heat into the space, and then it's going to shut off. It's going to turn on, and it's going to shut off. And what that's called is called short cycling, and that applies to the AC side too. We want to make sure that our system doesn't short cycle. We want to make sure that it runs its nice, span. It heats up the home nice and comfortably, and then it shuts off, lets the metal retract back to its state, and we let the system cool down. Then we apply heat, and we repeat the process. If we have too large of a system, it's going to go on, off, on, off, on, off, and that reaction is going to cause premature failure in the heat exchanger. Once we get a crack in the heat exchanger, generally that system is done for, unless you really want to replace the heat exchanger, and we then in turn replace the system. So it can be a very costly repair. It also shortens the lifespan of the equipment, and it's not energy friendly. So yet again, I'd almost rather have something that's a little bit undersized than oversized. Most equipment in homes are oversized. All right, the reason being is people were scared of putting in equipment that wasn't going to handle the load that we see from the Chicago weather, whether it's the polar vortex or if it's 100-degree days. People are scared and they want to make sure that the equipment's going to operate. When we size equipment, we're sizing it based on averages. So the coldest it usually gets in Chicago is 0 degrees. So our equipment is sized for that. If we have oddball days like a polar vortex where it's -20, our systems aren't going to be able to handle that cold of a temperature, and so the system is going to run 24/7. So if your system ever shut off during that polar vortex, if you remember, well then your system was probably too big. All right. The same applies for the AC side. We're designing for about a 90-95 degree day. Anything above that, it's just an oddball. We don't really size it up, and so that's where we can see system failures. With them operating too hard during those conditions. But regardless, proper sizing is crucial. So charging plays a role in that. Okay, undercharged systems, the compressor may operate continuously. It produces poor refrigeration, and moisture may be released from dryer into the system. Overcharged systems, excessive head pressure, and possible severe compressor damage. The severe compressor damage they're talking about, it's called slugging, where liquid refrigerant comes back through the system and winds up going back into the compressor. And that's why we're going to talk about superheat and subcooling to prevent that from happening. So subcooling is the amount of heat removed from refrigerant after condensing, okay? Equals temperature drop from liquid line to the condenser, determined by a thermometer and high pressure gauge with a PT chart, used to check charge in systems with a thermostatic expansion valve metering device. So basically, if we have a TXV on our system, we're going to test it with subcooling. If we have a traditional metering device, whether it's a piston or a capillary tube, we're going to test it with superheating. So what does subcooling really mean? All right, subcooling is the amount of heat removed from refrigerant after condensing. So after our refrigerant exits the compressor, it runs through a bunch of channels, tubes throughout that condensing system, and it releases that heat. All right, as we release that heat, the temperature of the refrigerant starts to drop. That temperature causes the refrigerant to actually condense. All right, remember the condenser changes the refrigerant from a vapor state to a liquid state. And once we hit that saturation temperature, we're going to keep dropping the temperature below that. Okay, so any amount below saturation temperature is our subcooling. So let's just say our saturation temperature for a refrigerant is 70 degrees. Okay, and I'm reading 60 degrees at my line set. Well, I know I've got a 10-degree subcooling. Okay, so checking refrigerant charge by subcooling. All right, so we're going to determine the condenser temperature. We're going to determine the liquid line temperature, and our subcooling equals the condenser temperature minus the liquid line temperature. All right, compare the calculated value with manufacturer specifications. So what that means is we've got our probe. All right, so that's just a clamp probe, they call it, and we've just got our thermometer right here. All right, it's clamp probe is sensing the temperature of the line, so the refrigerant running through the line is going to cause the copper to be the same temperature. All right, and then we're going to get a reading on our thermometer. This is where some gauges can do this automatically for you, but you have to understand the simple premise of how to do it. So we clamp our meter onto the line right next to the condenser, usually the liquid line coming right out of there, and we're going to get a reading. Our gauges then are going to tell us what our pressure is, and from there we're going to determine what our saturation temp is. So if we look at a label, that manufacturer is going to tell you the design subcooling for this system is 10 degrees Fahrenheit. All right, so let me just pull up a PT chart here for you guys. So we got different refrigerants here. If my pressure, let's just say, is 100 psi for 410A, I'm going to find my pressure. So roughly 100, between 99 and 101. So I'll probably be about, have a 32, maybe a 31.5 degree saturation temperature. So that means that if I were to put my probes on that liquid line and I'm reading 21, 22, somewhere in that range, I've got 10 degrees of subcooling. Okay, so my saturation pressure is 32. I subtract whatever my liquid line temperature is from that. In this instance, it's 10. It would be 22. 32 minus 22 gives me 10, and that's my subcooling. So I would know that my charge is correct. If my subcooling was higher than the design temp, well then I may or may not have an issue. Usually it's plus or minus 3 degrees. So the ideal range for subcooling is going to be between 7 and 13 degrees on this system. If I'm above 13 degrees and I'm at 14 or 15, 20, well then my subcooling is off. And I'm removing too much heat, or I have another issue. I may have an airflow issue. So I need to adjust the charge. And so I would, just to keep it simple, I would just remove the charge until my subcooling hit. So superheat is the amount of heat added to refrigerant after it has evaporated. Used to check refrigerant charge, so it's systems with capillary tube, systems with fixed orifice metering devices. So here we go, we got the thermocouple temperature probe again. The only difference is instead of going on the liquid line, we're actually going to go on the vapor line, and we're going to read our temperature before the refrigerant gets in the compressor, and we're going to do the same thing. We're going to check the temperature difference between the saturation temperature and the actual temperature. So It gets a little more complex for properly charging a system on Superheat, but I'll show you an easy way of doing it. So we have to measure 4 values. We measure the dry bulb temperature at the condenser. We measure the wet bulb temperature of the return air just before the evaporator, the pressure of the refrigerant in the evaporator, temperature of refrigerant at suction line service valve. So we calculate the superheat, suction line temperature minus the evaporator temperature gives us our superheat. All right. Why do we measure the dry bulb and the wet bulb? What is the dry bulb and the wet bulb? Well, the dry bulb is, they used to have a thing, used to be called a sling psychrometer. Okay, sling psychrometer was a tool that the technicians used to measure the humidity and how much moisture is actually in the air, and knowing that helps us adjust the charge. Okay, so the dry bulb was when this device right here would be whipped around. Okay, and once it was whipped around, it would give you a reading. That reading would tell you what the dry bulb temperature is. Okay, we would then wick this guy, put a little bit of moisture on there, and whip it around until you got a different reading, and that would be your wet bulb. Those 2 readings are critical because we can use a chart, I believe it's on the next page, to determine what our proper superheat is. So if we have a very hot house, say this house just, it broke down, the system broke down, and the house warmed up over time, it's 90 degrees inside the house, we want to be able to remove all that heat, but the system's going to take some time. And if we adjust our charge based on all of that heat that's in the home, by the time it adjusts and levels out to the proper temperature it's supposed to be, let's just say like 75, well then I'm going to have too much refrigerant in my system, which may in turn lead to slugging. All right, so we want to take these measurements to figure out what exactly the right superheat is based on the conditions. All right, if it's really cold outside and it's really hot inside, it's going to give me a different type of reading. So for example, if it's really cold outside, it's 60 degrees, and my return air wet bulb is, and say, well, let's just say it's really high, well then I don't have a reading here. All right, it's just not going to work properly. So let's just say we have a typical day. All right, whenever we're charging systems, we generally want to do them when it's 70 degrees. 65, you can get away with it. 70 is better. The warmer it is, the better it is. And we're going to measure the temperature. All right, it's a warm day, it's 80 degrees outside. We're going to measure what our indoor air wet bulb temperature is. So we'll get a reading, and let's just say it's a 70. Okay, so we've got a really hot house. We go down and we get a reading of 25. So 25 would be the recommended superheat. So every time you go into a home, you're going to be measuring out where you're going to measure out the dry bulb. You're going to actually do that outside right next to the condenser. You're going to measure out the wet bulb. The wet bulb, you try to get as close to the evaporator as possible. An air return where the filter goes, that's a really good location. If you can't get into that, any return duct really close to the evaporator is going to work as well, and that's going to give you a reading of what the superheat should be. Or you can use this app. Okay, sorry, this guy's a little bit blurry here, but what you end up doing with this, it's called the Emerson Check and Charge app. I personally love it. It works really well. You go into the app, you select the type of refrigerant that you have, you input the dry bulb, the wet bulb, and it'll figure out exactly what the recommended superheat is. So instead of having to carry around this chart with you, you just plug the numbers into the app, and it's going to tell you what your recommended superheat is. It'll also tell you what your current superheat is. So you put in your vapor pressure, you put in your suction line temperature, and it calculates all that information, tells you what your current superheat is, and what you should do. So in this instance on the right, we should be adding a charge. All right, my current superheat is 38. It's way too high. I should be at 18 based on the current conditions inside the home. If I have, a 23, where my recommended is 18, I'm in that ballpark. It's usually plus or minus 3 degrees, but according to the chart, we're off by 5. We're still okay. So that's just a simpler way of doing it. When we're charging, superheat, subcooling, it's the only way to really properly charge the system. If you start getting into inverter technology, really high-end equipment, the only way of doing it then is to weigh it in. Even on critically charged systems, meaning like flower coolers, walk-in coolers, things like that, they're going to want you to weigh the charge in. You can't really use the superheat, the subcooling, because it's just too small of a system where it won't be able to adjust based on conditions. So weighing it in, that's another way of doing it. On the side of the unit, it'll tell you, hey, this system requires 15 pounds, 3 ounces. Well, then that's what you would put in. You'd set your refrigerant on a scale and weigh it in until it hits 15 pounds, 3 ounces. If you don't know how much refrigerant is in the system, but you know that it's a leak, well then, if it's a critically charged system, you're going to have to pull out all that refrigerant, and you're going to have to redo it. So, pumping down a refrigeration system, pump down. Relocate system's entire refrigerant charge into a liquid receiver. Uses: it's for repairing leaks, adjusting low side pressure controls, replacing components. I think we talked about it last week a little bit, pumping down. So what we would do is we could actually use this for refrigeration side. Even though we don't have a liquid receiver there, we do have the coils of the condenser that we can store refrigerant in. So the proper way of doing this, we would, and I'm putting a disclaimer here, as long as my line set isn't terribly long, and whatever the factory charge is will fit in there, well then we can do this pump down. So we close off the liquid line service valve completely. We turn the compressor on. The compressor starts to pump, and it starts to pump and push all the refrigerant into the condenser. Once we get to a certain point where our pressure drops, because we're using a gauge as well, once we drop down close to 0, we wrench off the low side, and now most of our refrigerant is trapped in the condenser, and we can then do our repairs. There's a couple of different methods. So we have an active recovery, uses a recovery machine and draws out the system's refrigerant charge. So we're literally hooking up a machine to the condenser, and that machine is going to suck out all the refrigerant. Whether it's liquid or in a vapor state, doesn't matter, it's going to suck it all out. One little tip here, when you're using the recovery machine, it tells you that you're supposed to remove the Schrader cores. So you should have a core removal tool hooked up. You're going to pull the Schrader core out. You can then hook up your lines to the unit, and then you can slowly suck out the refrigerant. There's another method. We have the passive recovery method. Uses system static pressure. Basically, we're forcing vapor refrigerant into unpressurized recovery container, and this is used on smaller systems. Personally, I've never had to use the passive recovery method. I've always used a recovery machine with a recovery tank to get all that refrigerant out. The other thing too is I will bleed out my lines before I recover. The reason being is I don't want any impurities in my line. So as I hook up my gauges to the unit, I'll slowly bleed off a little bit of refrigerant through the end of it, so that I'm pushing out any air, any moisture, anything else that may be in my lines, and then I'll make my connection to the recovery tank. Try to keep it as pure as possible, because if I suck in any type of moisture, any air, well then if I'm going to reuse that recovered refrigerant, well then it'll get pumped back into the system. So I want to avoid that as much as possible. So we have a passive recovery method here. The internal pressure of the system forces the vapor into a recovery bag until the pressures equalize. I can do the same thing with the recovery tank. I can hook up my lines, it'll go into the recovery tank as long as the pressure of the system is greater than my recovery tank. If the compressor works, you can pump the remaining refrigerant into a bag. If not, lower the bag temperature, raise temperature of the refrigeration system. Simple way to lower the temp is just put the bag or put the recovery tank in some cold water, and then for the system you can pour some hot water on there. Any other method, there's some charging, not charging, but like heating blankets, things like that you can use. You could use like a heat gun. Never use a torch on any type of refrigerant. The reason being is you may actually cause that refrigerant to explode. So, vapor recovery, active recovery process. Vapor refrigerant drawn out of a system through a gauge manifold. Refrigerant pulled from low side and high side. So we're pulling refrigerant from both sides. Remember, Schrader cores are both removed. The vapor flows through an inline filter dryer. You want to use a filter dryer just to keep any impurities that may have collected from getting into the tank and contaminating the mixture. The vapor enters the recovery machine. Recovery machine's compressor pumps the vapor through its condenser. Liquid refrigerant flows into the recovery cylinder. So here we have just a simple setup of a recovery. So our system is off. That's critical. We're not going to be recovering refrigerant from a system that's running. All right. We're going to hook up our gauges to the liquid side, liquid line and the suction line. The cores have been removed here, so we don't have any type of restriction. We're going to open up both of our valves on our gauges to allow refrigerant to flow through the manifold into the recovery line. We have a filter dryer, the inlet outlet, and the cylinder. A scale is critical if you're weighing the charge, so that way we know how much has escaped. If we have a 5-pound system and I only pulled out 4, well, guess what? I'm missing a pound, and I can use that next time to know how much refrigerant I'm losing. So the next service call, if I were to do the same thing and I only lost, let's just say, or I lost another pound over the course of a year, well then I know my refrigerant leak is 1 pound per year. Liquid recovery, it's an active recovery process. Recovers liquid refrigerant from the high side of a system faster than a vapor recovery. Must be followed by vapor recovery to remove the entire charge. Do not use the liquid recovery method on heat pump systems or systems with less than 10 pounds of refrigerant. So unless you're working on some big commercial units, most residential systems don't hold 10 pounds. Most systems, they're running around 5, maybe 8 pounds. I think one time I ran across a system, really large, outdated system. I think that was at like 16 pounds for a residential, but normally 5 pounds is usually the norm. So here's our setup for liquid recovery. The low side valve is going to be closed on this application, so all we're doing is sucking in the liquid refrigerant through our system and going through the pump. You have a sight glass here. You can generally see the liquid refrigerant flowing through the sight glass, but you may or may not, just depends on how much liquid refrigerant is being pumped through. You may see some bubbles in there. Obviously, you may not even use a sight glass, but according to the book, this is how it's set up. The push-pull liquid recovery. Recovery machine creates pressure difference, creates a low pressure on the recovery cylinder, pulls vapor refrigerant out of a cylinder, pumps high pressure vapor into a system, pushes liquid refrigerant into a recovery cylinder, and the vapor recovery needed to complete the process. So what we're really doing is we're moving the refrigerant in one direction. Okay, so what we're trying to do is we're just trying to push this refrigerant through the system to get it to escape. Rather than trying to pull it all out, we're trying to get it to go into the system via the push-pull method, as it's called. This is great when you're recovering large quantities of refrigerant, commercial application. You know, we're not talking about single pounds, we're talking about tens of pounds of refrigerant at a time. And so this is where this would actually be very useful. All right. You're not going to see this on a residential side, but you will see this on the commercial side. Recovery tips: use large hose diameter. Use short hoses. Short hoses require less pressure, quicker vapor travel, produce less resistance and pressure drop. The more heat that you start to generate, as the refrigerant starts to flow through, it does create heat just because of the friction and everything else. That's why we try to keep our tanks very cool. The lower the temperature, or the less friction that you have, the lower temperature you're going to get. And so that's why they're talking about the shorter hoses. Remove the Schrader valve cores. Place an inline filter dryer between the refrigeration system and recovery machine's inlet port. After using the recovery machine to recover refrigerant from a burned out system, change the recovery machine's compressor oil. So what that means is if our system, all right, the system that we're working on, had a burnout, that means that oil and moisture mixed to create an acid. That acid ate away at the windings of the compressor and caused that system to basically fail. Well, that oil, all that moisture, all that contamination, the acid is in that system. And so when we're recovering our refrigerant, oil remains with that refrigerant because they like to bind with each other. And so that nasty gunk is going to come out into your recovery machine, and it's going to go into the recovery tank. So we want to make sure that we don't contaminate our system with that burnt out oil or the acidic oil that we have, and so we're going to clean it out. All right, recovery cylinder capacity: the maximum amount of liquid refrigerant cylinder can safely accommodate. So I know we talked about this last week. Weight of the volume of water needed to fill the recovery cylinder is water capacity. The fill level is 80% of the water capacity by weight. So the formula that we can use is W equals 0.8 times water capacity times SG, which is specific gravity of refrigerant. So off to the right here, it's telling you what the water capacity is, the 47.7. We also have the tare weight up here. It's telling you that the tare weight is 24.6. Basically, the tare weight of the cylinder is the weight of an empty cylinder. Okay, so if I have, let's just say, 54-pound cylinder, well, 54 minus 24 equals 30 pounds. So I have 30 pounds of refrigerant in that cylinder. Hopefully it's a 50-pound cylinder, because if it was a 30-pound cylinder, I'd be maxed out. So you want to use the scale. The scale is going to be adjusted to zero out the weight of the cylinder. And you can do this too, just to verify for your own benefit. You get a new recovery tank, you put that on the scale, and you can see how much that cylinder weighs compared to what the tare weight says. So here we go. We can do the tare weight minus the weight of the empty cylinder, and then we have the formula that we can use to determine what the max holding capacity of that tank is. We don't want to fill the whole tank up, remember, because that pressure is going to cause that tank to explode if I don't have any room for expansion. And so we've just got this quick little sheet here, and it's going to basically tell you the max amount of refrigerant to fill a cylinder at 80% of volume. So if we're talking about 410A, you know, I would hold 42.2 pounds of refrigerant in there. So WC minus TW equals the refrigerant weight. Recovery cylinder safety devices. Monitoring amount of refrigerant in a cylinder. So basically, we've just got a couple of things that we can use to make sure that we're properly filling our cylinders and we're not going over how much, you know, we're not going over the capacity. So there's a couple of types. A scale may sound a signal to stop or may close the solenoid valve. A liquid level switch or high pressure switch turns off machine when 80% full. Best to monitor and turn off recovery machine manually. Just a couple of safety devices you can implement when you're charging so you know when to stop. I personally never used one. I don't know of anybody that has, but they do exist, and they can make your job that much easier, especially if you're doing a lot of recovery. We can use these to really make our jobs easier and safer. Locating and repairing refrigerant leaks. Leak indications: low head pressure, low suction pressure, lack of cooling. So the first thing that you're going to come across when you come to a residential system is, you know, my system, it's not working. First thing I want to do is I want to make sure that I'm getting airflow. All right, I'm getting airflow inside. How do I do that? I'm going to check the filter. Okay, if I have a lack of airflow, that's going to cause my system to potentially to ice up. Well, why? Why is my system going to ice up? All right, let me pull up a PT chart again here. And I'm looking at R22, and I scroll down to about, let's see here, let's just say 57, 58 PSI, okay? My temperature is going to be 32 roughly in, my saturation pressure is 32. Okay, so my refrigerant's running at 32 degrees at 57.5 PSI. So, excuse me, sorry. So what that means is if I were to decrease the airflow, all right, the heat that I'm removing from the space, and all I'm doing is sending the refrigerant around to get colder and colder because I have no heat to warm up that refrigerant. So my refrigerant pressure is going to start to drop because I'm removing extra heat at the condenser. And that refrigerant is going to keep going back in the cycle. It's going to get colder, it's going to get colder, it's going to get colder until it gets to the point where it hits 32 degrees. Once it hits 32 degrees, I'm going to start creating ice, okay? Why? Because I have moisture in the air. That moisture is coming in contact with a 32 degree evaporator coil, and now I'm going to get ice developing. That's all attributed to lack of airflow. As long as I have heat coming across that coil, I'll never be able to drop to that low temperature mark. All right. Traditionally, you're going to see your temperatures probably hovering around the low 60s to high 70s, starting out with R22. The reason being is I've got a nice safety cushion here, 40, 41 for my temperature, and that's, you know, about 8 to 10 degrees above freezing. So in case I do lose a little charge, I'm not going to turn my system into an ice machine. Now what happens is, if my pressure starts to drop, well, so does my temperature, because we have a pressure-temperature relationship. So if I was normally running at 70 psi and I developed a leak, well, I have less refrigerant for it to flow through the system, so my pressure is going to start to drop eventually until I get to 32 degrees. Well, then again, I'm going to start icing over. Evaporator might start, may start icing over. The condenser could start icing over. It just really all depends. But we're going to have icing conditions. Now, the third option at icing over, because there's different ways our system can ice over, but it's all related to the pressure temperature. If my condenser is plugged up and I have no airflow, well, I may, that refrigerant is just going to keep running through, looping through our system yet again. It can't get rid of heat, it can't absorb heat, and so it's just going to get colder and colder until it finally ices up. So we want to make sure that we have proper airflow for our system. All right, if we don't have proper airflow, then we're going to have low suction pressures, low head pressures, and we're going to get a lack of cooling. Those are leak indicators, but they can also be attributed to airflow. Locating leaks. All methods include a pressurized system. Okay, so we got to find the leak with refrigerant in the system. We have to have pressure in there. If we have no pressure, we're not going to find a leak. All right. If we have no pressure, we're going to have to add pressure into the system. Okay, we're going to use nitrogen. It's an inert gas, and we're going to pump our system full. We may use a little bit of a tracer gas in there, so we may pump a little bit of R22 or R410A. Let that get into the system a little bit, and then we're going to pump it full with nitrogen. We're going to look for a couple of different things. We can use, well, you know what? Here we go. Let's just go through the slides. I'll get to the other topic here in a second. So we're going to create a positive pressure of 5 to 30 psi. All right, so that's how we're going to do that. We can do like maybe say 5 psi of refrigerant, and then we can do another 15, 20, 25 psi of nitrogen. The unit label is going to tell you what the test pressures are. Usually for 410A systems, it's about 150 psi. Some may be greater. It just really depends. Never use fuel gases or oxygen. Use inert gases such as nitrogen or carbon dioxide. Once we fill that system up, we're then going to listen for leaks. That's the simplest way. We're going to go by the evaporator. We're going to go by the condenser, and we're just going to look for, listen for some hissing. If no hissing develops, we can use our soap bubbles. We can spray all the joints that are available to us with soap bubbles. If the soap bubbles don't give you any indicator, it may be something else. One of the condenser coils may be leaking. One of the evaporator fins may be leaking. One of the brazes on there. It's hard to say. We can use a leak detecting device, ultrasonic. We can run that through. We can use dye. We talked about the dye to see what's going on. But in this procedure, or this, what they're talking about here is pressurizing the system. We want to use like a refrigerant sniffer. That's why we've put that little tracer gas in there, or we're going to use the soap bubbles. Do the best we can to really find it. You may get to that point where you still can't find the leak. You may have to isolate the system, meaning you're going to close off maybe the condenser from the evaporator side, or you're going to literally take off or cut off one side of the system, pressurize it, and see if it's that side of the system that's leaking. Let's see. So yeah, you can do the evacuate the system and charge the system with inert gas and trace amount of specified refrigerant used if the leak cannot be found. Always use all methods of leak detection. EPA allows refrigerant release as leak test gas. So if I put a little refrigerant in that tube and I'm trying to find that leak, the EPA says that that's okay, and I can just release it into the atmosphere. So pressure testing with inert gas. We've got our pressure regulator, pressure relief valve, hand valve. I've never seen a hand valve. Usually I see the system here with the pressure regulator, the relief valve. All this I never see connected. It's usually you're connecting your regulator to your gauges, and then your gauges are going to fill the system. All right, we're not going to exceed the recommended pressure by the manufacturer. The reason being, we may cause an explosion. The compressors are rated to a certain pressure. Anything above that may cause them to rupture. I would not want to be standing above, a 600-pound burst or a 800-pound burst, whatever the case may be. If recommended testing procedures are not known. Do not exceed 170 psi when testing with carbon dioxide or nitrogen. Generally, 150 is what I was taught. The book says 170. Be sure pressure regulator is accurately calibrated, and your relief valve should open at 180 psi. That's great. Mitsubishi systems, the mini splits, they want you to test up to 600. I think Daikin, they wanted you to test up to 550. All that information's on the data plate on the side, so you know that. But residential-wise, for 410A, 150 usually gets the job done. All right. Preparing to repair leaks with brazing. We always want to recover the refrigerant from the system before we do any brazing, because if we apply heat to refrigerant, the pressure is going to go up and it may potentially cause an explosion. And we're going to make sure that our system is completely empty, especially on the side that we're brazing. And then we're going to purge the system with nitrogen. All right, what we're going to do is we're going to let a little bit of nitrogen flow through our system. The reason being is we don't want carbon to develop on the inside of our tubing. If that carbon develops on the inside of our tubing, it's going to start to flake off, and it's going to plug up some of these little screens or the TXV that's on there. So we're always flowing nitrogen when we're brazing. Epoxy resin, not a big fan, but it does exist. Some manufacturers, depending on the repair that you're looking for, they're going to want you to do an epoxy repair. So this is what we have. It's a thermosetting polymer that forms a strong adhesive used to repair cracks and leaks in evaporators and joints. Used with aluminum, steel, copper, plastics, two-part system is most effective. Basically what you're going to do is you're going to take epoxy 1, epoxy 2, you're going to mix them together using the mixing sticks, and you're basically going to apply that to the area, and you're going to let it just harden, and it's going to form a nice stiff joint or repair. The emery cloth and the methyl ethyl ketone, you're going to use the emery cloth to clean the area, and then the methyl ethyl is just going to be used to clean it after the sanding, just to make sure that it's nice and clear. You have no type of residue or gunk on there preventing the epoxy from adhering. When using epoxy resin, avoid contact with the skin, so use gloves. In case of contact, remove epoxy, clean skin with rubbing alcohol, wash thoroughly with soap and water. Evacuating system. Very important. Again, we've been talking about this for the last couple of weeks. Using micron gauges, we're going to remove all the vapors, gases, fluids from a system. So fluids, or meaning moisture, water that may have accumulated in there. If you have any other type of fluid in there, it may evaporate, it may not. We're not going to be evaporating oil, so keep that in mind. Whatever oil's in there, it may not come out. When do we evacuate? After the refrigerant has been recovered, but before the system is charged. So we've opened up our system, we've made a repair, we put in something, whatever the case may be, and maybe a new filter dryer. We're ready to seal up the system. We're ready to fire this guy up. We've done our pressure testing. All right. When we're doing a pressure testing, by the way, usually most manufacturers, they want you to put the inert gas in there. You're going to fill up the system to 150 psi, 170 according to the book, and then you're going to wait. I would wait like a minimum of an hour, and you're going to see if there's any type of change in the pressure. The other thing I do too is I'll go around with soap bubbles and I'll spray my joints that I brazed to ensure that I've got a nicely tight joint. After that's all done, I then remove that nitrogen from the system. I just let it escape into the atmosphere, and now I'm ready to pull a vacuum. Before I completely allow the system to empty dry, I'll save maybe a PSI or two in there just to keep from moisture from entering into the system, and then I'll hook up my vacuum pump and start pulling everything out. So there's a couple of ways that you can evacuate. There's a deep vacuum and the triple evacuation. Okay, I don't like this setup here. All right, the reason being is I'm using a T-fitting, and every single one of these spots right here is a place for a failure. If I'm going to do anything, I'm going to put my micron gauge as close to the condenser as possible. So for example, somebody may hook up their line to the liquid line. If that's the case, then you can hook up your micron gauge to the suction side, and you can start pulling your vacuum via the liquid line, and your micron gauge is going to read. I attach my micron gauge directly to the core removal tool, and it does a really good job of reading what my microns are. Never put your micron gauge on the pump when you're pulling a vacuum. It's good to test either your micron gauge or your pump. You can do that, but as I'm pulling a vacuum on a system, I want it as far away from that pump as possible. Otherwise, I may be contaminating my micron gauge with oil. So the effects of leak and moisture on an evacuated system's pressure. So if we were to have a leak on a system, okay, what will end up happening is we pull a vacuum, all right, we pull it down to what the manufacturer says, and let's just say it's 250 microns. Well, after a certain amount of time, I've shut the pump off, I'm at 250 here, and the system's isolated, right? Nothing else is getting in, nothing's open. My pressure is going to rise. If my pressure continues to rise as the time rises or keeps increasing and it doesn't stop, well then chances are I have a leak in the system. If I were to have my system, off 250 microns, and after, let's just say, 5 minutes, the system stops and stabilizes and holds, and we'll just say it's 1,000 microns, well then I know that I have moisture still in the system. Different systems are going to have different amounts of moisture. You can have two 2-ton systems, all right, one at one home, one at another, but they may have different line sets, and they may have different amounts of moisture that were in them, depending on what happened, how long they were exposed to the elements, and so forth. So if your micron level doesn't increase, let's just say above 1,000 microns, you generally know that your system's okay. If it starts to increase above 2,000, maybe even 5,000, then you may have a leak. It's not uncommon for very large systems, once you shut that system off, that micron level jumps up to 2,000, or maybe even 3,000. The reason being is you just have so much moisture in there, it's just going to take a very long time to remove it. I was doing a Mitsubishi system, and with it I had literally 3 line sets attached to one unit. And traditionally it would take me maybe about 15 minutes, 10 to 15 minutes to pull a vacuum on a residential system. I think I was pulling a vacuum for over an hour to try to achieve the proper micron level. And the reason being was I had 3 line sets, all long, they were exposed, to the atmosphere for a little bit, so moisture may have got in there, and it just took a really long time to bleed it all out. So don't be in a hurry. Make sure that you evacuate your system. So we have a deep vacuum. Vacuum pump pulls a vacuum of 250 microns or deeper. We use service ports and access ports. Do not use piercing valves, and the remove the Schrader valve course. So remember when we were covering our system, we still just leave the valve course on there, and once we're done pulling a vacuum, then we can put the Schrader course back in and take those valve core removal tools off. I usually pull to 250 microns. I don't go anything below that. 250 seems to be the accepted number. What I'll do is I'll pull 250 microns, Some manufacturers say 350. Read the book, the manual that comes with it. Either way, pull it down to 250, and if I don't go over 500 microns in the course of a minute, then I'm okay. So, so you continue until no moisture vapor remains. Use a vacuum gauge to determine if system has moisture leaks. Vacuum should hold at 500 microns for at least 1 minute. So, if I'm charging a system, bring it to 250. My microns stay at 430 after a minute, slowly going up after that, but a minute's passed, but I'm generally good. As long as, if it goes over 500 microns in that minute, well, I still have moisture that's boiling off. So I want to make sure that we have, we're adhering to this deep vacuum. This is the industry standard now. We're making sure that we have deep vacuum. We can also, so here's an indicator or a display of how a deep vacuum works. We've got our service valve, low side, our high side. We've got our tubing connected to our vacuum gauges, or our gauges. I don't use gauges. Gauges are another point of failure, all right? So all I use is a nice big thick tubing. It's actually meant for vacuum. We don't want to use our traditional hoses. The reason being is while we're pulling a vacuum, we're actually going to get intrusion through the hoses of atmospheric pressure, and so that's going to really mess up our vacuum. So we're going to use vacuum hoses. We're going to take our vacuum gauge, and we're either going to put them on the high side or the low side and have our hose on the other side, or we're going to have a core removal tool right here that our gauge is going to sit on. Okay, putting a T-fitting in like this, don't like it. Same thing with the gauges. That's another way for it to leak. So we pull all our vacuum through the hoses to the pump. This one has a solenoid valve. You may or may not use it, depending on the application. Commercial applications, if you're doing a really lengthy vacuum, you may need it. Triple evacuation. Vacuum pump pulls a vacuum of 1500 microns 3 separate times. So what happens is we're going to start our system. We're going to pull a vacuum. We're going to pull to 1500 microns. Once we hit 1500 microns, we're going to introduce nitrogen gas, clean nitrogen gas. We're going to raise the pressure until it hits 0 psi. We're then going to pull a vacuum again until it hits 1500 microns again. We're going to introduce nitrogen, and then we're finally going to pull our nice deep vacuum. All right. Depending on who you talk to, I mean, the book says 1500. When I was talking with Mitsu, I think it was drop it down from to 3000, then you go to 1500, and then you go and you pull your deep vacuum. So they wanted it spaced differently. The book says drop it down to 1500, 3 times. It's up to you guys, but that's just the premise of a triple evac. What you're doing is you're not absorbing moisture. Some people say that nitrogen absorbs the moisture that's in the system. That's not really true. What you're really doing is you're pushing out the moisture out of the system, if anything's contained there. So you're just putting in dry nitrogen, and that's just going to push out anything that's really stuck in there that you're having a hard time getting out. If you're having a hard time pulling a vacuum on a system, then I would recommend doing triple evac. Yeah, so this one, it tells you the moisture remaining in the system is absorbed into the nitrogen. Last I heard, that's not true. You're just pushing the moisture out. All right. So the setup for the triple evac, very similar, except for we're using a nitrogen cylinder that's going to be attached to our gauges. So what I do is I'll actually take my gauges and hook them back up to the core removal tool after I'm done pulling a vacuum. So I'm going on and off, but at least then I don't have a point of failure with all this that's going on in here. Charging a system. We're going to add refrigerant to a refrigeration system. Must be done after the system has been opened, repaired, and evacuated. So, symptoms that charging may be needed. We've got the frosted evaporator, like we were talking about. We've got that pressure is dropping, so we're getting the temperature that's right around 32 degrees of our refrigerant, and so we're getting ice buildup on there. Okay, that could also be a sign of not enough airflow. So just because you have a frosty condenser or a frosty evaporator doesn't necessarily mean that it needs charge. That's what a lot of technicians may default to. It could be an airflow issue. Okay, so low head pressure, low side pressure. You have a leak, system short cycles. So general guidelines for charging a system. Liquid charging is faster, but it involves risk. Whenever we're hooking up our systems for charging, we're always charging on the suction side. No matter if we're charging via a vapor or a liquid, we're always charging on the suction side. Most systems should be vapor charged. The only time we don't charge as a vapor is when we're dealing with blended gases, like 410A. We're going to charge it as a liquid to keep fractionation from occurring, and we're going to make sure that we're getting the correct refrigerant blend going in. Vapor charging, cylinders upright. Liquid charging, turn the cylinder upside down, and we're going to charge refrigerant into the high side. I don't charge into the high side. The reason being is when the system is running, okay, especially with 410A, our pressure are going to get into the 300, possibly even 400 range. If our 410A tank has been sitting there, our charging cylinder has just been sitting there, and it's been a cool day, well, guess what? That pressure is going to be higher in the system than it is in the tank. So we'll never be able to overcome that difference. And so what we have to do is we really have to charge on the low side. We have to do it delicately because we're introducing liquid refrigerant into the low side, which may cause slugging. So we have to be careful when we slowly bleed the refrigerant into the system. So vapor charging, we've got our tank set up, going into the manifold, and we're going to go into the low side service valve. If the system is off, and this is for something that the system's not running, we can definitely put refrigerant into both sides, okay? It's only going to speed up the charging process because the refrigerant's going to go from the bottle into the system until it equalizes. Generally, you're not going to be able to put enough refrigerant into a system that you're charging that's completely evacuated. The system's going to hold more than this bottle's able to give off. Now, if you're using one of the big bottles, then it's possible that the pressure would equalize and there'd be too much refrigerant in there, but from a 30-pound size, no. You're generally going to have to charge the system while the system's running. So liquid charging, here we go. If the system's off, this is perfectly fine to do. After our system's running, we always charge on the low side. Changing refrigerants. Local building codes may specify the types of refrigerants that can be used. Retrofitting, updating existing systems to new standards, replacing specific components. We talked about retrofitting. Everybody did their paper on retrofitting or on the refrigerants. People talked about retrofitting applications. Not a big fan of it, as we discussed. Just another bottle to carry on the tank or in the van, and it's just it's like putting a Band-Aid on the system. We don't know how long it's going to really last. If it's a brand new system for whatever reason and they're having issues, well then this may be an option, but most systems are going to be over 10 years old. It may just be better to replace than to retrofit. Identify refrigerants. do not identify by color or smell. Use a refrigerant analyzer. With the changing of tanks and everything else, you know, we're going to have all gray tanks, so that color scale is almost going to be null and void. There's still tanks out there, but just know that everything's going to be gray. Don't try to smell, I guess, refrigerants. Yeah, I won't go into that too much. Modifying and replacing system components. Contact manufacturer for details. Yeah, the manufacturer always may want you to do certain things. It's nice to have Google at our fingertips to be able to pull up different manuals for different manufacturers and see what their practices are. But all of the charging stuff that we discussed today is pretty standard when we're talking about all the systems. They all work off the same premise. One manufacturer may want a different subcooling temp than the next, but it just all depends. And so that's it.